minerals. There's a lot of minerals out there that have iron influence. The ones we're going to focus on tonight are your magnetites, your hematites, and your limonites. And those are the kind of the main ones. There's a couple other like I also am going to talk a little bit about pyrite. Right, this is iron sulfide. So this is basically, instead of an oxide, a bit of sulfur was added in the process. So it's created the beautiful golden sheen, which just gives it the name fool's gold. I also brought a piece of a slice of iron meteorite. So if you've never, I'm sure you've probably seen these in the show. If you want to hold it, touch it, lick it, play with it, look at it, be like, okay, this is what it looks like when you cut a piece of iron meteorite. One of the telltale signs is the wind's pattern. So this has been etched so you can see that pattern. As they enter into the Earth's atmosphere, it creates this kind of crissy-crossy pattern where you get basically these crystallizations of iron as well as nickel and some other stuff. It's mostly iron.
Meteorite heating up?
Yeah, the meteorite heating up, entering the Earth's atmosphere creates this pattern that's quintessential meteorite. There's a lot of people try to fake it with like etching, but it's obvious when it's real. It's real. Until China figures out how to fake that, which is who knows when. But I have a piece up here. Feel free to let's pass this around. You guys can look at it. This gets us all warmed up with the concept of iron. Raise your hand if you've ever tried to chase a shooting star as a rock hound. Am I the only one? Okay. Where you see a shooting star and you're like, okay, triangulate the mountain range here and that mountain range here. Get an azimuth.
I have done it in like.
Yeah. It's like, I would love, what's that? No, never found one. never, not for trying. One day I will. One day I will. That gives you kind of a pure form of iron. I also, because iron is a huge industrial mineral, obviously. Probably one of the most important industrial minerals in the history of humankind. So usually we don't see it in its pure form though, because it's not as durable as when you process it and you create steel. So by creating steel, you add in the carbon, the nickel, all these other minerals, which give it its toughness and durability. But at its core, I decided to buy 1 centimeter cube of iron, so that it's at least you can play with the test with. You can look at it. Okay, does it magnetize? It obviously does. It's pure iron. And then you go down the list of purity. So this is 0.999 fine. You go down the process of reduced purity of iron. Then you start to get into basically those minerals that we're going to talk about tonight and how you can determine what they are. Right. So the next step in kind of the devolution of iron, like you think about our Earth, the core is made up of what? Iron, right? It is the most abundant mineral on our Earth. Can you imagine our Earth if we didn't have iron? Can you imagine human history if we didn't have iron? What would it be like? Think about the early man taking iron and turning it into a tool kind of concepts, right? Where did they get it? How did it form? When you out in nature, it's obviously quite pretty abundant in southern Utah, but it's also abundant throughout the Earth. It is in the crust, the third most abundant. So it's the third after silica and then aluminum. Those are a little bit more abundant than iron in the crust. Now, the reason why it's the most abundant on Earth is because the core is a piece of iron. That's what gives it its most, the top dog status. However, it is the second most commonly used metal today, after aluminum. So aluminum is more common now to be used, but it's still industrially, it's the most important, one of the most important things. Yeah?
It's in your blood too.
It's in your blood. We're going to talk about that. It's kind of fascinating. Yeah. Yes, aluminum is much softer. Yeah, it's much softer, lighter, lower specific gravity. Yeah, it's much. It's people use it more now because it's lighter. Really, like if you look at modern industrial practices, the reason why aluminum is used is because it doesn't oxidize like iron. Hence, when you start to go down the purity levels, it's due to primarily oxidation, which is what we'll talk about. Like you look at how much oxidation has happened on iron. Yeah.
I'm going to refute that.
You're going to refute it. All right, what you got?
Okay, you take pure aluminum, you scratch it, and within a millisecond, it's oxidized already.
So aluminum does oxidize,
It oxidizes just.
maybe not to the extent of iron, but it does.
It doesn't oxidize and, collapse like all the iron structures are going to do in this nation in a couple.
Yeah, it's more durable and it's less susceptible to the
Yeah,
oxidation.
very much so.
Cool. Thanks, Gordon.
It does oxidize.
We'll do an aluminum. We need to do an aluminum one. We need to find a raw count for aluminum. That'd be kind of cool. But anyway, so we talk about how it presents. We know that it's very abundant. It's very abundant here, and then we look at okay, so in its pure form, it looks like a metal, like a typical metal. It's it's this shiny silvery color. But as you add more oxygen, okay, so how did it form? We know that it exists in the earth typically in large bands. They call them, it's iron band formations. Basically, they form in large bands, typically primarily as a sedimentation. It can form in all three methods, though, not just sedimentary, but also igneous, because a certain amount of iron exists within magma and lava as an igneous stone, and it also is metamorphic. So you think about the iron pyrites of Australia. Have you ever seen those big, large stones that they've cut? And you get these bandings of iron, like tiger's eye style, or the maramambas of the world. And you get this wicked kind of pattern where it's just been tortured over the millions of years. It's no longer this nice pattern of banding. It's this tortured metamorphic process that turned into a metamorphic stone. So that is another way that iron can be found in nature. But primarily it's found as a sedimentary stone that's interacted with ancient something. Who can tell me what ancient something it interacted with to cause the oxidation? Any ideas? Any takers? What did the iron form battle with in nature? What created the oxidation events which turns it from iron to magnetite to hematite to limonite? Water. Think about your car. Think about your car with no paint on it. It rains, it's going to go rusty like that, right? The iron inside the steel will, start to oxidize. So you think about how that happened over a long period of time. Then you basically are removing or you're replacing a solid homogeneous iron structure with iron oxide. That coming from the interaction with water. Typically ancient salt or seas with salt in it or fresh water. So that's where you'll typically find them, stacked with other formations where there was an ancient seafloor. A lot of times with limestone, like the stuff you see around here, basically you'll see it between limestone layers where you have these different times in geologic history where there's large water formations, where then iron may have precipitated and interacted with the water and created the iron oxides which exist today. And so who can tell me what the highest iron content mineral is out there that's not iron pure, but the next one down the chain, most iron? It's abundant, but there's one that has a higher iron content. Starts with an M.
Meteorite.
Well, I guess meteorite. That doesn't form naturally in Earth, but yes, I think meteorite has the highest iron content.
Magnetite.
Magnetite. And that's why you can determine out in the field if you found a piece of magnetite. This one's fairly easy because it actually shows the iron crystallization of magnetite. This comes out of Three Peaks area, and you find magnetite. Why is it called magnetite? Magnetic. Easy way to figure out in the field. Okay. If you take your plate, your porcelain plate, ceramic plate, which has a hardness of 7 to 9 on the Mohs, depending on how hard that ceramic is. Probably not a 9. That's going to be a ceramic talent. What I like about white ceramic or white porcelain is it gives you an accurate color representation of your iron minerals or your minerals because it's on white as opposed to being on the back of some modern ceramic tile that's weird color that might throw you off. Space shuttle. But a typical ceramic tile we have here is harder than anything that kind of forms naturally. It's typically 7 and higher. So you take your porcelain plate, your ceramic plate, and you can do your scratch test. Let's say you don't have a magnet on you, but you kept the free one I gave you tonight in your car. You go out there and you go, is this hematite? Is this magnetite? Is this something completely different? You know that hematite's going to give you maybe a little more color. Magnetite, it's hard. It gives you like a black gray. Gives you like a blackish gray. So,
Are they always, like the one that my dad has here is all smooth on top? Are they always like so smooth like this?
nope, very seldom are they.
Oh, okay.
A lot of times you'll get them in pieces. So what you're showing is actually probably hematite, a botryoidal hematite, which gives you the botryoidal. We'll talk about hematite in a minute. But the more pure form naturally here, kind of formation-wise in our geologic history, besides meteorites, is magnetite. Okay, magnetite also comes in great crystalline structure, like I said. And if you go rock counting up in Iron County, Three Peaks, Iron Mountain, Granite Mountain, you guys have been there recently?
I'm using limonite.
Did you find any magnetite crystals? I know you did. You sent me some pictures. Yeah, of some of this, and then some of them had apatite on it. You're wondering what the apatite was. So I'm going to pass this around. There are small crystalline structures inside of this magnetite. That's apatite. So this game, just take a look at that. I'll put a magnet on this. Okay, so what has the highest iron concentration of an iron mineral naturally here? Magnetite. Magnetite. What is its streak? What is its streak color? It's hematite. I think this is probably hematite. It might be magnetite. If it streaks black, it's a lot darker. Let's streak this and find out.
Okay.
Streak it.
You have to get the other end. Like this end. That's brown.
No.
So if you look at the actual chemical, the molecular structure of magnetite, it has an extra iron atom in the chemical composition compared to the hematites. So it has two or three iron atoms with 4 oxygen atoms. So it gives it a higher, basically it has more, the molecular structure is larger, and it has a higher, that's why it's stronger. Its hardness is a 5 to 6, which is pretty impressive considering that's the hardness of steel. So it's the reason why it's such a hard mineral. It's almost, it's about 72% iron. There are also fossils that it forms in as well. So you have some magnetic fossils that have magnetite in it. It's typically octahedral crystals, but it can also form as a rhombic dodecahedral crystal as well. Yeah, the octahedral crystals are typically formed in a thermal process involving like geothermal stuff. Typically 1 centimeter size or less, you'll see. So, which is typically a size, you don't get much bigger than a centimeter in size. Next mineral below magnetite, if we remove an iron atom and an oxygen atom, we get hematite. Hematite is the most abundant iron mineral and the most commonly used iron mineral for industrial purposes. The easiest way to tell the difference between magnetite and hematite, well, there's 2 easy ways. We already talked about how to determine magnetite, so what do you think the easiest way to determine what hematite is versus magnetite? Streak?
It doesn't magnetize.
And it's less magnetic. If you put it in water next to a magnetite, you might get a slow attraction. But typically, in the field, if you have a magnet, it'll be like, it'll give you like the magnetite lodestone feel, like it's sticking to it really good. Okay, so this is botryoidal hematite. So then we go to streak it. Reddish brown streak. As a hardness, it's going to be slightly softer. So now you have 2 iron atoms and 3 oxygen atoms. They'll occasionally form crystals, rhombohedral lattice crystals. Sometimes you get this botryoidal formation, which you see like an agatization, this bubbly top. This is how a lot of times they sell it. That's when you see the bubbly top, it's typically a hematite as opposed to a magnetite. And it's streak. What's the color streak? Reddish brown. Okay. All right. We're learning something. I think it forms in a similar kind of process. It can form through sedimentary, igneous, or metamorphic processes. You'll see it in all 3 of those as well. That's typically not. So if we continue to degrade this iron molecule, what's the next step? What's the next? And there's actually, limonite is kind of a common term for all of the minerals that kind of follow a little bit next. So we can see staining like this on something, we start to see the limonite staining, right? The yellow ochre color. So when you go to test it, get this reddish, this yellow orange color, right? This is going to be very common. It's a very common mineral that you see. It's a much softer stone as well. So whereas you have your magnetites, they're up there at 5 to 6 on the Mohs. Your limonites, the hardness is variable, but ranging like 1 to 5. Or sorry, yeah. So it's in the lower end of the scale. The telltale giveaway is that color. Now occasionally you'll have, before I keep so that's alignment. So we take a quick break, do some cool raffles, and then we'll kind of talk and we'll have maybe a chat about it. Maybe have more questions. The question was asked: is the desert varnish a form of iron? Yes. So you get a mineral, maybe a chalcedony, that'll be out in the desert, and it'll be this reddish brown, and it's literally like probably less than a millimeter thick, and we call that desert varnish. It is an iron oxide. So let's real quick talk about pyrite. So if we talk about pyrite, what was the atom that combined with iron that wasn't oxygen? If anybody remembers.
Sulfur.
Sulfur. So this is 2 sulfur, 1 iron, FeS2. So ferrous sulfide, which you have, which gives you fool's gold. So it's iron so let me say this correctly, iron disulfide, because di being 2. My chemistry teacher from way back when would smack me because it, missing the actual correct pronunciation. But it's a couple sulfur thrown on an iron, and it creates a really beautiful crystalline structure. Lots of different kinds, isometric, dodecahedral. You got a lot of different crystal structures that happen with pyrite. Some of them don't even form a clean structural pattern like that, but are gorgeous. So if you're interested in seeing a couple of different types of patterns, I've got a couple up here. But it can degrade, and does anybody remember, before I wrap this up, what happens when sulfur gets replaced with oxygen? What do we call it?
Limonite from pyrite.
Good enough. Good enough. Limonite from pyrite's good enough. Yeah. Limonite after pyrite. I don't know. It's just basically, it was pyrite, became limonite. Because it's no longer technically pyrite. There's no more sulfur in there. It's just oxygen and iron, which is now limonite, because it's the most basic form. It's also the softest. So let's, for funsies, I don't know if I scratched this one earlier. That's the color we got. Kind of a lighter yellowish red. This is where you get that yellow ochre, right? The oldest cave paintings on Earth are yellow ochre. Now that's a good foundational stance for whatever else we talk about, or for whatever else you find out rock counting, because you're going to find a lot of iron minerals out there, especially in southern Utah.